Howdy, welcome to Math 153, Elementary Statistics. My name is Lance Curtis, and this is the lecture for section 6364. So you can see the first section that we're going to cover today covers the application of normal distributions. So we're going to take what we've learned from the standard normal distribution in section 6.2, and we're going to apply that to some real-world applications. This is where the standard normal distribution really gains its power. The key concept here is to illustrate how to work with non-standard normal distributions. So the mean is not going to be 0, the standard deviation is not going to be 1. It may be one or the other, or maybe both of them together. Typically it is both, but any way you slice it, we're not dealing with the standard normal distribution. However, we can use a simple conversion method that allows us to standardize any normal distribution so that we can use the methods of the previous section to then fill out the full power of statistics with normal distributions. So let's dive in. Standardizing normal distributions basically requires a simple equation to convert random variables from non-standard normal distributions into z-scores that are associated with standard normal distributions. Here's the equation. Z equals x minus mu over sigma. So our z-score for our standard normal distribution is equal to the difference between our random variable, x, and the mean of our distribution. And then that distance divided by the standard deviation gives us z. This equation should not surprise us. After all, remember how we defined z-scores earlier. That z-scores were the number of standard deviations a value is away from the mean. And that's exactly what this equation provides us. X minus the mean, this gives us the distance from the mean, and by dividing it by the standard deviation, it converts that distance into quote-unquote units of standard deviation. So this is the formula for converting random variables to z-scores. Now, we can also rewrite this equation so that if we want to go the other way and have a standard deviation, a standard normal distribution that then converts to a non-standard normal distribution, we can go the other way as well. We just rewrite the equations you've seen above in terms of x. This gives us x equals mu plus z sigma. So if we want to go from a normal distribution to a standard normal distribution, we use the z formula, z equals x minus mu over sigma. If we want to go back the other way, we use the conversion formula, x equals mu plus z sigma. So here's an example to illustrate how this conversion works. Let's use the standard and non-standard normal distributions that we were just looking at to illustrate. So for a given non-standard normal distribution, okay, notice we have a mean value of 1010, and each one of these values that you see to the side represent a single standard deviation. So standard deviation will be 20. So we're going to apply this conversion process to convert from this non-standard normal distribution to the standard normal distribution you see here. And to do that, we're going to make use of this table that we see here at the right. So first we're going to select a random variable to convert. It doesn't matter where we start, but let's just start on the left end. So we'll take this leftmost value of 950, and we're going to convert this to a z-score on the standard normal distribution. So we'll put the 950 there in our table for our first row for the non-standard normal distribution side. Now we apply our conversion equation. Here's our conversion equation. We're going from the non-standard to the standard. So our conversion equation is z equals x minus mu over sigma. Plug in what we know. So our random variable, that's our x, that comes from our normal distribution. The non-standard one, it's 950. The mean is 1010, and the standard deviation is 20. So when we evaluate this out, 950 minus 1010 gives us negative 60. Divide negative 60 by 20, and we get negative 3. So this is what we put into our table under the z column. This means that the z-score of -3 corresponds with the random variable of 950 in our non-standard normal distribution. We repeat this procedure for any values that remain that we want to convert over. So if we want to convert the other values that we see here in the table, we just start with the next one down, 970, and we start again. Here's our conversion equation. Plug in what we know. Evaluate this. 970 minus 110 is going to be -40 divided by 20. That gives us a -2. So then we fill in the z column in our table, -2. And we continue on this way for the remaining random variables in our non-standard normal distribution, converting them all with equations, filling in the table. And now we have a correlation between the standard normal distribution and the non-standard normal distribution. That correlation becomes very, very useful when we're asked to calculate probabilities and percentiles. As we saw in the previous section, 6.2, we can very easily use a z-score table or software to calculate probabilities and percentiles for standard normal distributions. But now that we have the ability to convert a non-standard normal distribution to a standard normal distribution, we can easily calculate probabilities and percentiles for non-standard normal distributions, as well as the standard ones. This becomes very, very powerful because we're relating random variables to z-scores, which are then related to areas under the curve, which are then related to probabilities. Now, if we didn't go through this process of standardizing normal distributions, we would have a very painful time trying to find probabilities and percentiles for non-standard normal distributions. In the first place, our z-score table that we've been using so far applies only to standard normal distributions. And in fact, if we wanted, we could make our own table for a non-standard normal distribution. But because there are an infinite number of normal distributions that we could specify, we would need a separate table for each one of those specific distributions. Wow, already that's hurting my head thinking about all the work that would go into making all those tables. Ah, that's painful. Of course, to make the values that are in the tables, we would have to perform integral calculus to get each one of those individual values in the table for our z-score table. And we would have to run this calculus equation every time we wanted a table value for z-score. So you can see that having this simple conversion process is a whole lot easier than having to go through all this work making a separate table or even performing the integral calculus for one value in that table. Let's look at a specific example where we can apply this. There is a social club called Tall Clubs International. It's a social club for tall people. If you're a woman, you must be at least 7 inches tall in order to join this social club. So, given that women have normally distributed heights with a mean of 63.8 inches and a standard deviation of 2.6 inches, what percentage of women satisfy this height requirement? In other words, what we're really asking is, how exclusive is this club if you're a woman? All right, well, let's apply our procedure and see what the answer is. First, we're going to convert the random variable to a z-score. We do that with our conversion equation. So z equals x minus mu over sigma. And we plug in what we know. So x is our random variable. That's the 70 inches. That's the requirement. Subtract out the mean of our distribution and then divide by the standard deviation. And we evaluate that expression and get 2.38. So this is our z-score that corresponds with our random variable. Now that we have the z-score, okay, that actually corresponds with the area on the far right of our distribution, which we would expect being a positive 2.38. What we're looking for is the shaded area in red. Okay, we want to know what percentage of people are actually over that requirement, because only the people that are taller than 70 meet the requirement. So we want the area to the right of that z-score. The next step then is to quantify that area to the right of the z-score. We do that looking at our table. Here's an excerpt from a z-score table. The appropriate row, we look for 2.38, which gives us this value here, 0.9913. This then is the area to the left of the z-score. But as you can see by looking at the distribution, we want the area to the right. Well, we can still use the area from our table to calculate the one that we want. We just have to take the complement. So the probability that x is greater than or equal to 70 is the same probability that z is greater than or equal to 2.38. And that's going to be the complement of the area that we read in the table. Remember, the table is listing the area to the left, but we want the area to the right. So we have to take the complement of what we see in the table. Subtracting 0.9913 from 1 gives us the area we're looking for, 0.0087. This then is the probability that a woman will be able to join, a randomly selected woman will be able to join Tall Clubs International. Less than 1%. I'd say that's pretty exclusive. Now, if you're a man, the requirement's a little different. To be a man and join Tall Clubs International, you need only be 74 inches tall. And I would say there's a higher proportion of men that meet the requirement for joining than there are women. So it's not exactly evenly split gender-wise, but, you know, if you're a woman and you're looking to associate with guys that are also tall, and you're tall yourself, maybe it turned out to be a good deal for you. As you're working these problems, don't confuse z-scores and areas. Some students get these confused. Okay, remember, z-scores and areas are living in the same jungle. They are related, but they are not the same animal. Z-scores are distances along the horizontal scale. Remember the definition of z-score, the number of standard deviations away from the mean. So it's a distance. It has only one dimension to it. Z-scores can also be positive, meaning we can have z-scores to the right of the mean, or they can be negative if they're left of the mean. Areas, on the other hand, are regions under the normal distribution curve. Regions have two dimensions to them, a length and a width. Because they represent probabilities, areas are never negative. So where z-scores can be positive or negative, areas cannot be positive or negative. Areas can be only positive, never negative. That's because that density curve always stays above the horizontal axis. It never dips below. Because it never dips below, that area is always going to be positive. Furthermore, areas are representing probabilities, and we know that probabilities are bounded between 0 and 1. Likewise, areas will also have the same bounds, bounded between 0 and 1. Therefore, areas can never be negative, only positive. Furthermore, look in the z-score table. The z-scores appear as column and row headings. They're on the sides and the top of the table. But the areas themselves appear in the center, the body of the table. So yes, we are looking at evolutionary cousins living in the same jungle, but they are not the same animal. So try not to confuse z-scores with areas. Also, try to choose the correct side of the area under the curve. Some students, they can set it up right, but instead of looking to the area to the left when they should be looking to the right, you know, they choose the wrong side. So they choose left when they should choose right, or they choose right when they should choose left. If you read the wording of the problem that's presented to you, it should be pretty clear as to which side you need. If you just think about it for a moment, and don't rush yourself, just think about it for a moment, it should be pretty straightforward which side of the curve, or the area under the curve that you're looking at, the left side or the right side. Remember that z-score tables usually list the area to the left of z-scores. So if it's the area to the left that you want, you can use the number that's right there in the table and run with it. That will do for you. However, if you need the area to the right, remember to use the complement. Subtract the area you find in the table from 1. That gives you the area to the right. Let's look at another practical example of converting between non-standard and standard normal deviations. So engineers that work in the aircraft industry have a very daunting design challenge. They have to balance design parameters for functionality with minimizing weight. And minimizing weight is a huge thing in aircraft design, because the heavier your aircraft is, the more fuel you need to get your aircraft off the ground and keep it airborne. Well, fuel costs money. In fact, aircraft fuel is one of the largest expenses for operating and maintaining aircraft. So it's in your best interest when designing an aircraft to minimize weight as much as possible. This is why for many years aircraft was designed with light metals like aluminum alloy rather than more common high strength materials like steel, because aluminum weighs a whole lot less than steel for a part with an equivalent amount of strength. Nowadays, you see the trend in the aircraft industry is to move towards high-grade composite polymers. So, in essence, we're making airplanes out of plastics. It's new technology. It hasn't been around for around. But plastics, I mean, if you can get the strength up, which they've been able to do with some of these new composite plastic structures, you can actually achieve sufficient strength levels with plastics. And plastics weigh a whole lot less than aluminum alloy. So there is a move on the cutting edge of the aircraft industry to move towards even lighter and lighter materials while not sacrificing the strength. Well, you can make the inside cabin of the aircraft, if you want to minimize the weight, you want to make that as small as possible. But you want to make the ceiling height tall enough so that most people can actually fit through without having to hunch over. So, given that men have normally distributed heights with a mean of 69.5 inches and a standard deviation of 2.4 inches, what ceiling height will allow 95% of men to stand erect? In other words, they can stand up straight without bumping their head on the ceiling. And we want 95% because that includes most everybody. Again, it's 95% related to our range rule of thumb, as we've seen in the previous section. Well, first, what we want to do is use the probability to find the area under the curve. Note that we're not given, as we were in the last example with Tall Clubs International, we're not given a random variable to start with. We're given the probability and asked to find what the random variable is. So we're going to follow the procedure that we just illustrated in reverse. So we start with the probability that they give us, 95%, and use that probability to find the area under the curve. So here's our distribution. We want 95% of the area to the left of whatever our z-score is. We want the area to the left because people that are shorter than the ceiling height that we're looking for won't have a problem. It's only the ones that are going to be taller. And we want 95% of the people not to have a problem. So this 95% of the area under the curve is going to be the area to the left. We can convert this area into a z-score very easily by using a z-score table. So here's a snippet from a z-score table that shows the row that we're really interested in. We look for the area of interest, 95%, which appears between two values that are listed on the table. So when a value appears between two values that are listed, we can interpolate the column headings to get the appropriate number for the hundredths place. And when we do that and reconstruct our z-score, we get 1.645. This means 1.645 is this boundary area for our area right here on the right. So we know what the z-value is on the standard normal scale, but what about the non-standard scale? What's this random variable here. What does this z-score convert to? Well, you should be able to see that the next step then is going to convert our z-score to our random variable of interest. We're going to use the conversion equation, x equals mu plus z sigma. Plug in what we know. So our mean value is 69.5. Our z-score, which we just determined, was 1.645, and our standard deviation is 2.4. Punch this out on your calculator, round to the nearest tenth, and you get 73.4. This, then, is the ceiling height that we want to have, the minimum ceiling height that allows 95% of men to stand erect. And this is what the engineers will design to, because to make a greater ceiling height requires more material on the outside to boost the ceiling up higher. And you want to minimize the weight, so you want to use the smallest height that you can get away with. This, incidentally, is why for many years aircraft were manufactured with the seats and the adjacent rows so close to each other, because they're trying to minimize weight so that they can minimize cost of operating the aircraft. So as we can see, there's a conversion process involved here. And all the problems that you're going to be asked to solve, you're either going to be given one or the other end of this conversion process. You're either given a random variable that asks to find a probability, or you're given a probability and asked to find a random variable. If you're given the random variable, use this equation to convert your random variable to a z-score. Then convert the z-score through a z-score table or software to get the area under the curve. That area under the curve is then your probability. Conversely, if you were given the probability and asked to find a random variable, just do that same process in reverse. Remember, the probability is the area under the curve. Use the area under the curve to get a z-score from a z-score table or software, and then once you have the z-score, you can convert to the non-standard normal distribution with this equation, x equals mu plus z sigma, and then you'll have your random variable that you're looking for. So either way you go, you're going one direction or the other, but these are how all these different elements are related. And this is a conversion process that really allows us to calculate easily probabilities for non-standard random normal distributions. And that's the type of distribution. Most normal distributions that we see in the real world are not standard. So this procedure allows us to convert easily to the standard normal distribution, and from there to get the area under the curve and hence the probability of whatever it is that we're looking for. That brings us to the end of section 3. So now we're going to jump into section 4, looking at sampling distributions and estimators. Basically what we're looking at here is individual statistics all have sampling distributions. And basically what that means is we're going to take samples from a larger population, and then we're going to take statistics of those samples, and those statistics, those groupings that we have, are going to form a distribution, which we call a sampling distribution of whatever statistic it is that we're measuring. It's the mean, the variance, standard deviation, and others. So we're going to see that some of these statistics are better than others for estimating population parameters. Remember, one of the things that we're interested in with statistics is being able to take a sample that's characteristic of the population so that we can then characterize the population without having to survey or take a census of everything in the population. We only want to take a small part of it and then use that small part, which is our sample, to characterize the entire population. So let's get more into how that is actually done. Normally, when we go through these sections, I give you the actual theory or, whatever, and then we actually look at practical applications. For this particular section, I think it would make more sense to you to do that in reverse. So we're actually going to look at an actual application for what we're talking about, and then you actually have the application to lean back on. I think the definitions that we need to cover in this section will make more sense. So let's look at something we can all understand. Rolls of dice. If we wanted to look at the population for rolls of dice, we would have to look at every roll we could possibly make. So our sample space would contain an infinite number of outcomes. That's the population of dice rolls. We don't want to have to, make every roll we could possibly make in order to get characteristics of the population. We want a sample of the population. Every roll that we actually do make. So our sample space is going to contain a finite number of outcomes. And it's going to be one that's small enough that we can actually manage it without having to sit around and roll dice forever. Now, the outcomes of our rolls, we're going to collect them together and they will form a distribution. Okay, this distribution will then give us characteristics about the population that we're trying to characterize. Now, as I said before, we do want to characterize the population. We don't want to sit around forever rolling dice. I mean, life is short, and I don't know about you, but I got better things to do with my one life than sit around rolling dice forever. So, how do we characterize the population without actually taking all of the outcomes in the population? We want to take a sample of the population, but we want to do it in a way that the characteristics of that sample resemble those of the population, because then we can take statistics on the sample and then apply those as appropriate to the population. So let's design an experiment to test this out. Because the key question is, how large of a sample do we really need in order to say we've got a large enough sample to characterize the population? How many dice rolls must we make to have a sample large enough to resemble the population? This is the key question. Well, first, what is it that we're expecting the mean value to be? What do we expect the mean value of the population of dice rolls to be? Well, recall that the mean value is the expected value. As we've seen before, we calculate that by summing up the product of random variables and their associated probabilities. So to help us with that calculation, we're going to make a table. And so we have here a column for the random variables, a column for the probabilities, and a column for the products of those two quantities. So first, let's identify our random variables. When we roll a six-sided dice, we could roll a 1, a 2, a 3, a 4, a 5, or a 6. So then these outcomes represent our random variables. Now, what are the probabilities that any one of these could occur? Well, the probability that we roll a 1 is 1 out of 6, because there's one number out of 6 possibilities. So 1 out of 6. The probability of rolling a 2 is also 1 out of 6. And likewise for the remaining random variables. They're each 1 out of 6. Notice that this is essentially forming a uniform distribution because we have a set of random variables, so distributed between 1 and 6, and they all have the same probability of outcome, which is 1/6. This is definition of uniform distribution. To get the products, we simply multiply the x by the probability. So 1 times 1/6 is going to be 1/6. 2 times 1/6 is going to be 2/6. And on down the line, so we fill up the entire column. So now we've got the products of all of our random variables and their associated probabilities. Now the expected value is going to be the sum of all of those products. So if we take these products and add them together, we get 21/6, which when you divide out is 3.5. This then is the expected value, what we would anticipate the population mean to be. So this essentially says this is our target, this is what we're shooting for. Now the question then becomes, how are we going to approach that target? How are we going to get there? So let's decide we're going to roll the dice 5 at a time, because you can sit there with one dice, but then taking samples of 1 at a time is, first of all, it's going to take you a lot longer to get to where you want to go, and second, we want to actually calculate characteristics along the way. So we're actually going to start with calculating the mean value, since we're talking about the mean. And it's easier for a mean value to be more meaningful if we have more than one. So let's just roll 5 at a time. We can calculate the sample mean for each of the 5 dice that we roll after each trial. And then we can add that to the other trials we've already done to calculate a new sample mean for the entire sample space. Eventually, our sample is going to become large enough to resemble the population. And at that point, the sample mean should approach or target the population mean. So now we've set up our experiment. Let's actually go through and see what happens. So we roll 5 dice for the first time. And here's what we get. A 3, a 2, a 1, a 2, and a 2. So let's make a little table here to see how we're progressing as we move towards our expected value. So we've got one trial. The mean of the outcomes in that trial is 2. We take 3 plus 2 plus 1 plus 2 plus 2, we get 10. 10 divided by 5 is 2. Our sample size only has these 5 outcomes in it, so our sample mean is going to be the same as our trial mean. Let's roll the dice second time. Then we get these results out. We get a 1, a 6, a 4, a 3, and a 1. So now we get to update our table with a second trial. The mean of our trial outcomes is 3. We take 1 plus 6 plus 4 plus 3 plus 1. That gives us 15. 15 divided by 5 gives us 3. But notice that we now have 10 outcomes in our sample space. So our sample size is increased to 10. Therefore, when we're taking the sample mean, we include all 10 of these values in our mean value, our average. So when we do that, we get a sample mean of 2.5. Oh, look, now we're moving closer to that 3.5 value that we're expecting to get. Let's roll the dice a third time. So now we get these 5 results out. Update our table as appropriate. And we can see that the trial mean could be all over the place. Okay, but the sample mean is inching closer and closer to that 3.5 value that we're looking for. Rolling the dice a fourth time gets us these results. So updating our table again, the trial of our means, if we take these 5 from the fourth roll and we average them out, we get 4.6. But now we've got 20 outcomes in our sample space. So averaging all 20 of these values out gives us 3.45, which some people would look at that and say, hey, that's reasonably close to our expected value. But what we really want to get is a whole lot closer than a number that we could just round up to and say, yeah, we've got the expected value. We want to get the expected value itself, or get very, very, very close to it. So we're going to need to run some more trials. So to continue the experiment further, I actually sat down and rolled the dice 20 times to get 100 outcomes. When I did that, I could then calculate not only sample mean, but also other statistics like the sample variance and the sample standard deviation. And these are the values that we get. Now, we can see that we're still a little ways from the actual expected value that we're looking for. And in fact, rolling it more times, we actually went down a little bit. Recall from the previous slide, the sample mean was 3.45. Now we're down to 3.44. So we're going to have to roll this dice quite a few number of times before we get to our actual expected value. So how many more times are we going to have to roll this? I mean, like I said before, I'm lazy, and besides, I only got one life. I don't want to spend it doing nothing but sitting around rolling dice. So this is where simulations come in. It's a good thing we live in the 21st century because we have the power of modern computers that help us to actually simulate simple events like rolling dice. This way, we don't have to actually roll 5 dice over and over and over again. Okay? We actually get the computer to do that for us. Computers are great at generating random numbers, and they can plug those random numbers into an algorithm that then converts the result to a number between 1 and 6, inclusive. Computers are also great at counting and collecting data. So we could sit there and we could actually do the counting and the collecting, but it would take us a lot longer. Computers are much more adept for that task. So we're actually going to get results much faster than actually performing it ourselves if we use a computer simulation. And fortunately for us, StatCrunch has the ability to perform simulations for simple experiments like rolling dice. It's built into the software. So let's see what would happen if we go 1 and 2 orders of magnitude above where we stopped physically rolling dice. So if our sample size is increased from 100 to 1,000, what do our sample statistics look like? Likewise, if we go to a 10,000 sample size, what does our sample mean, variance, and standard deviation look like? Well, conduct a simulation, and here's what we get. Okay, so StatCrunch produced these results. We go to 1,000. Look, we've already targeted our mean, 3.5. If we continue rolling and get 10,000 in our sample space, then 3.49. So we got down just a little bit, but we're still right there next to the expected value of 3.5. So if we chart all those out as we're actually going through, the proportion of the dice rolls in our sample space that are greater than the average expected value of 3.5, this is what the graph would look like. So as we roll more and more, we start getting a greater proportion of the averages of our rolls greater than 3.5, which brings the whole average closer and closer to 3.5. Eventually, though, we start approximating this straight line. And the straight line is basically marking the limit. Now, technically, this is not really a straight line. It's really a line that's bobbing up and down, up and down, up and down, up and down. But when you zoom out and actually get the full picture view, this is essentially a straight line. And this is marking, saying that, yeah, you know what, we've actually reached our limit. We have achieved our actual expected value. Notice that half of the 10,000 outcomes are above the mean and half below. Okay. Again, this is not exactly 50% because as this line was going up and down, up and down, up and down. But 0.4935, that's really close to 50%. And that's what we would expect to see, half above and half below. Now notice that, as I said before, this line is essentially straight as you go out. Where does it start becoming that more or less straight line? Well, it starts becoming that right around here, which when we go down to our graph corresponds to around 1,000 trials. And so, look, this is what our table was telling us. We have a sample size of 1,000. We've already reached our actual expected value. And going much further than that doesn't really show much improvement towards meeting that expected value. The number that we get is going to be right around that same expected value. So it doesn't really make much sense for us to run 10,000 trials when all we need is 1,000. This is for the sample mean. Now, if we look at a distribution of individual outcomes in our sample space, we get a uniform distribution. This is what we would expect. Remember when we were calculating expected value that we had the same probability for each possible outcome? That's the definition of uniform distribution. And that's what you generally see when here, as shown, you make a distribution of the individual outcomes in our sample space. You get a uniform distribution. But in accordance with the idea of taking simple random samples, if we group our outcomes into groups of 5, and then take each of those samples of 5 outcomes and put them into a distribution, we get a normal distribution, as you can see here. And notice that half of the outcomes are above the mean and half are below. In fact, we see that same proportion for each of the distributions, and that's what we would expect. Half are above, half are below. Half are above, half are below. Now, if we were to actually group not just sample means into the distribution, but actual sample proportions, so what proportion of the outcomes are even or odd, or what proportions of the outcome are greater than or less than the actual mean value, we would also get a normal distribution, just as we would if we were doing this distribution for the actual sample means. So the means and the proportions give us similar results. So then we could say that the sampling distribution of the sample mean is the distribution of all possible sample means with all samples having the same sample size n taking from the same population. So purposes of our experiment, our sample size was 5. So we had 5 dice every time we rolled. So each one of those samples or trials for the sample size is 5. And we were taking those groups of 5, those samples, from the same population, which is the sample space that contains an infinite number of outcomes, every possible roll that we could have. Now, because of this, we see that the sample means target the value of the population mean. Okay, as we increase the number of outcomes in our sample, so our sample space gets larger and larger, as that happens, the mean value of our sample tends to target or approach the population mean. This means that the mean of the sample means is the population mean. Or another way to say it is that the expected value of the sample mean is equal to the population mean. And this is what we saw with our experiment. We also note that the distribution of the sample means tends to be a normal distribution. Okay? Now, just as we saw on the previous slide, everything that we saw with proportions matches what we've seen with the means. So because they have the same features, we can say that the sampling distribution of the sample proportions also targets the value of the population proportion, and that distribution is also normal. If we look at the variance, we see a slightly different picture. Note that the distribution that we have is skewed. This is not a normal distribution. This is a skewed distribution. And this is what statisticians would describe as being skewed to the right. Okay, remember this is one instance in which statisticians are thinking backwards from most people like you and I. So, I look at this and say, well, the bulk of the distribution is on the left side of the graph. So I would say the distribution is shifted to the left. But statisticians aren't looking at where the data is. They're looking at where the large tail created by the skewness in the distribution is residing. Here the larger tail is on the right. And so this larger tail means that they would say that the distribution is skewed to the right. The variance for infinite outcomes would be 2.9. Okay, so we need to actually go up to 10,000 trials before we start targeting the sample variance. The population variance with the sample variance. If we stop at 100, yeah, we've already reached our target for the sample mean, but we're not quite there with the sample variance. We're actually overshooting a little bit, and that's okay. I mean, as you get closer and closer to the expected value, you're going to go up and down, up and down, up and down. But yeah, we actually do need the 10,000 trials before we get to where the sample variance is going to be targeted with the sample. However, we do note the same thing that we've seen before, that about 50% of the values in our distribution are below the mean of 2.9, and that 50% are above the value of 2.9, our mean value. This is what we would expect to see, and this is what we do see. So the sampling distribution of the sample variance is the distribution of all possible sample variances with all samples having the same sample size n taken from the same population. So we have the same qualities that we had there before, but the difference here is that although the sample variances target the population variance, meaning that the mean of the sample variances is the population variance, the expected value of the sample variance is equal to the population variance, the distribution of the sample variances will not be normal. It tends to be skewed to the right. So there are some estimators that we see that target their population parameters very well. These are what we would call unbiased estimators. So the mean, the variance, and the proportion are sample statistics that target well their respective population parameters. Note that when we're talking about proportions, there's a little bit of nomenclature that's different from what we would normally see. So Normally when we're talking about a population parameter, we use a capital letter, and then we use the corresponding lowercase letter for the corresponding sample statistic. Here, we're actually, because the capital letter P, we want to use P for proportion. Okay, that sounds good. That sounds all right. But we've already known that we use the capital letter P to represent probability. So we can't use it also to represent population proportion. So some statistician got the bright idea, okay, since the capital letter P is already taken, why don't we use the lowercase letter p? Okay, so now this is going to get a little confusing. We're using a lowercase letter to represent the population. Be that as it may, created another conundrum. Well, if we're using the lowercase letter p to represent population proportion, what do we use to represent the sample proportion? And so someone got this bright idea that we'll just use a P with a caret on top. When I say caret, I'm not talking about the vegetable C-A-R-R-O-T. I'm talking about this little accent mark, caret, C-A-R-A-T. Now, because this caret on top of the P looks like a little hat, this character is often referred to as P hat. So we're going to use P hat to represent the sample proportion, lowercase letter p to represent the population proportion. Now, just as there are unbiased estimators, some sample statistics are very biased estimators. These sample statistics do not target well their respective population parameters. And you see some listed here. You have the median, the range, and the standard deviation. These sample statistics do not target well their respective population parameters. Now, one thing to note about the standard deviation is that often we will use the sample standard deviation to estimate the population standard deviation. But we have to have a large enough sample size to do this. The reason why we can get away with this with a large sample size is that the larger the sample, the smaller the bias in the bias estimator. Well, as it turns out, if your sample size is sufficiently large, the bias you get from the standard deviation becomes small enough to be practically negligible. So with a sufficiently large sample size, you can use the sample standard deviation to estimate the population standard deviation. But as a general rule of thumb, the standard deviation is grouped with the median and the range as being a sample statistic that is a biased estimator and does not target well the population parameter. Now, as you're going through and you're working problems, it's going to be really tempting to compare these values for the sample and the actual population and then say, okay, well, they're close enough, they must be targeting well. And what I would encourage you to do is to just ignore that. Don't compare the numbers. Even though it may seem like that's the thing you need to do, the way to get the right answer in these problems is to understand mean, variance, and proportion are unbiased estimators. They target well their respective population parameters. Median, range, standard deviation are biased estimators because they don't. That's just stick with that, and that will see you through. So, to round up here, some observations on sampling. We've already noticed the importance of taking simple random samples, and in fact, that's exactly what we were taking with our dice rolling experiment. Simple random samples. You want to be careful to use an appropriate method of sampling because some sample types, like voluntary response or convenience sampling, can very easily give us wrong results. So you want to make sure you're sampling appropriately. But on that note, the question is raised, should we sample with or without replacement? Well, if we sample without replacement, that tends to avoid wasteful duplication. Okay, especially when we have the same item that we're selecting more than once. However, for most real-world applications, we want to sample with replacement. If you're wondering why do we want to sample with replacement, well, there's a couple of good reasons. The first is, if your sample size is relatively small with respect to the large population, then it makes no significant difference whether we sample with replacement or without replacement. Remember from assignments that we had in previous chapters that, if our sample is less than 5% of the whole population, then we could actually, assume that the calculation was, that the events in the calculation were independent and not dependent. And that made a big difference, because if we can assume that the events are independent, then that means that the calculations to calculate our probabilities become much, much simpler. So, yeah, we actually do want to sample with replacement, even though sampling without replacement avoids wasteful duplication. We actually are sampling small enough with respect to large populations, and we can do this. So it actually makes sense to make that assumption that the events are independent, even though they may not be, and therefore simplify our calculations out. That rounds up this lecture for sections 6.3 and 6.4. If you have any questions, you know how to get a hold of me. Otherwise, I will see you in class. Thanks for watching.